Yeah, thank you so much. Thank you so much for the introduction. Very happy to be here. As just mentioned, we are a security company. So in contrast to all of the other speakers today that will be telling us how we should be doing things, I'm here to tell you how not to be doing things. Joking aside, how do we go forward? This one? Yeah. It doesn't. Oh, okay. Okay, cool. In Veridise, we're strongly believers that sharing our experiences and stories from our audits is it's the #1 ingredient to ensuring a more secure Web3 future. So today we're gonna see what can go wrong during ZK development. We're gonna see how to avoid such mistakes, and also we're gonna end up with some tips and tricks to ensure that our ZK projects are more secure in the future. So to begin with, I'm going to start with our setup for the day, just to make sure that everybody's on the same page. When I talk about a ZK audit, I mainly talk about a system that has two components, an off-chain component that computes a proof to a very lengthy computation, and then there is another component that lives on-chain that validates the proof. So generally speaking, the first step in these systems is for the off-chain component to fill out some values for some variables. And then the on-chain component is going to validate that these values satisfy a set of predefined constraints. And generally speaking, in ZK jargon, the component that does the off-chain stuff is called a circuit. So whenever I refer to a secret moving on, it will be something like this. And next, let's see how ZK developers build applications these days. It used to be the case that you had to be a cryptographer. Luckily for us, now there are several ZK frameworks and languages that come in a wide range of either DSLs or libraries hosted in a general purpose language. Then from that, you magically get transformed to a set of polynomial constraints. Then you have some crypto magic happening on the back end, and you automatically get a prover and verifier. The prover is the off-chain component. The verifier is the on-chain component. So for the purpose of this talk, we're going to focus on bugs that happen on this side of the diagram. The other side is a story for another day. OK, now that we have the setup in place, let's see how things can go wrong. And we're going to start with the most infamous category of bugs, that of missing constraints. So on a high level, how these bugs manifest, they begin by the ZK developer forgetting to introduce some constraint in the circuit. Then an attacker can essentially exploit that, create a malicious proof, post it on the chain, and steal funds because there wasn't a constraint that should have been there. So let's go and see some specific bugs that we have seen in past of our audits. A small parenthesis here, since our goal here is to teach what can go wrong and see how we can prevent these things. I'm not going to reveal any development team. I'm just going to give a vague description of the application and reveal details that are relevant to the bug. So for the first bug, we have an application built using Circom and Solidity. It was an AVM privacy layer, and they have this UTXO-based infrastructure. And the user had a bunch of keys. One of these keys was responsible for creating nullifiers for a UTXO. So typically, a nullifier was going to be a function of the UTXO and the public key, the public nullifying key. So the circuit had as an input both the private nullifying key and the public nullifying key. So naturally, a requirement here is that we want only one nullifier per UTXO. If you can create multiple nullifiers for the same UTXO, you can double spend. So the bug in this specific application was that one of the circuits wouldn't validate that the input public key was the one corresponding to the input private key. So naturally, now an attacker, since this constraint was missing, they could pass like an arbitrary public key for a private key and create multiple nullifiers for the same UTXO. So then, like, they essentially could start like spending the same UTXO over and over again. Okay, so this sounds bad. So how do we prevent that? Luckily, the solution here is like very easy. We just write negative tests. And what I mean by that, you need to write a test that tests the bad case. So you essentially are going to pass a random public key for a certain private key and a UTXO. And then on the other end, you will expect like the whole thing to fail. Okay. Okay. So let's now move to like a bit more trickier bug that like involves some math. For the next application, we audited a recursive ZK verifier that was implemented in NARC. And in the core of this application was like a library that was implementing arithmetics on the Goldilocks field. So the bug here was like a very subtle misconstraint on the module that was calculating the inverse of a field element. So if you're not familiar with the inverses, it's like very simple. All they state is that like if you have, the constraint that you need to introduce is like if you have your input and its inverse, which is going to be the output of like that component, you want to ensure that if you multiply them in the Goldilocks field, then the result is going to be 1. So that was the constraint actually that like the developers had written, and it seems to check out, right? However, there is like a small caveat here. If these two values can fall outside of the Goldilocks field range, then this constraint can have multiple satisfying assignments. Essentially, you can prove for the same input that it has like multiple inverses. And because this library was sitting at the center of like the whole application, it can introduce like multiple critical bugs because it was being used around a lot. So how can we prevent this type of bugs? Unfortunately, the answer here is not as clear-cut as before. So first of all, it's harder to like detect these type of bugs and fix them. But what we can do is like document assumptions of our modules. So this way, if somebody is building on top of our modules, they can essentially see what necessary checks they need to do. And also, pencil and paper proofs can also help. You essentially prove like a mathematical theorem that your constraints are correct. And one positive note here is that like part of these proofs can essentially be automated. And here at Veridise, we have a verifier called Picus that can verify part of this proof that like essentially states that your constraints are deterministic. So essentially, it checks that like for the same input, you cannot have like two outputs that satisfy the constraints. And if you want to learn more about Picus, you can follow that like QR code. Okay, so these are like the bugs that I'm gonna display for this category. The question is, should we care about these bugs? The answer is yeah, because they are kind of like the logical bugs of like ZK development, and it shows us like from the data that we have collected in Veridise, it shows that like developers haven't really adjusted to this new programming paradigm called ZK. And when they miss a constraint, this bug tends to be critical. And 90% of the missing constraint bugs we have found at Veridise, they were either high or critical. OK, let's move to the next category of bugs that I'm going to talk about today. Here is what we call the DeFi ZK snafu. And what do I mean by that? So one way these type of bugs can manifest is the following. So generally, you want your ZK and DeFi component to be in sync. And sometimes they can get out of sync. And one way that this can happen is like by forgetting to validate state. So of course, off-chain components, they don't have access to on-chain data. So whenever you want to have like a circuit that operates over on-chain data, you have to pass the current data to the circuit, then get the output generate the proof and post the overall proof on-chain. And then the on-chain component is responsible for validating that the proof that was generated over that circuit was consistent with the state that the on-chain component has. So one way these kind of like out of sync errors can happen is if the on-chain component forgets to validate that the proof was generated given the current on-chain state. So let's see a specific example. So here we had like another application written in Circum and Solidity. We had, it was like a recommendation platform where like users could interact like privately. So whenever they had to interact with the system, they had to encrypt their balances and either deposit and withdraw. So you encrypt your current balance, you encrypt your new balance, you post it on chain. So the smart contracts have like multiple routes that people could like, deposit and withdraw. And some of these routes were like missing the validation check that like the proof was generated with the current balance. So a sequence on this system, it was completely feasible, where a user could say, I start with balance 0, I deposit 1, then the app says, okay, your balance is 1. And then they could say, okay, now my balance is 1,000, I'm going to deposit another one, and then they get like a balance of 1,001. Okay, this also sounds really bad because, like, if the DeFi component doesn't check all necessary things, things can go extremely wrong. So how do we avoid these type of bugs? We go back to our old good friend, like negative test. However, here we need to write a negative test that exercises both the ZK and DeFi component. And given our experiences, we see this type of like negative tests to be less often than others. And at Veridise, we also develop like novel static analysis techniques that they essentially go over your on-chain logic and essentially like check if your contract's essentially missing any of these checks. If you're interested, happy to talk later on. We have a booth, you can find us there. Okay, so like this is like, this is the last bug I'm gonna show you today. But like ZK and DeFi components can get out of sync in many other ways. We have like things like proof replays, unless you are like in Elio where like, proofs cannot be replayed, arithmetic denial of services, field overflows, things. So the list goes on and on. So generally speaking, like these type of bugs affect like systems where the on-chain component and the off-chain component are written in different languages. And what we have noticed in general is that if your developers are out of sync, then there is a high chance that your system is also out of sync. Okay, so I'm not going to talk more about bugs. I want to leave the talk with like a more positive note and see what we can do to kind of like improve security in the Web3 space in general. But the first question is like, should we really care about ZK security when it comes to Web3? And the answer, I think it's an emphatic yes. So the bugs that I touched today, it's like, it merely scratches the surface. We have like many more categories from privacy leaks, cryptographic misuse, overflows, and so on and so forth. And from all the audits that we have done at Veridise, we have noticed that ZK projects are twice as likely to have a bug, and 80% of our ZK audits will contain at least a critical or a high bug. So what should we do like moving forward? So of course we need to invest into security and invest to security early. So whenever you go out and design a system, you have to be security conscious from the design phase. So you have to create a very realistic threat model. So you need to know what things are possible at the framework we're currently developing on. And you need to make sure that your design essentially prevents all of these attack vectors. And also, you need to be diligent when documenting things and document important invariants of your system and make sure that they're being enforced system-wise. And I want to close with like a quote like that, security is not a destination, it's just a journey. You need to test thoroughly, make sure you write negative tests to avoid silly bugs like the ones that we saw earlier. Also make sure to integrate automated security checks in your CI/CD, and of course, partner up with a reputable and experienced security team to make sure that everything checks out. And with that note, I'm gonna close and feel free to answer any questions.